Great, greetings. Okay, right. There we go. Okay, greetings. This video is going to be about flexible AC transmission systems. Flexible AC transmission systems. Okay, we are just going to touch on the learning outcomes. Okay, the learning outcomes is just basically a way of guiding us, is to say what should be important and what shouldn't be important. Okay, so that's why we are going to go through the learning outcomes. So here goes now. After studying this unit, you should be able to do the following now. You should be able to sketch the basic topologies and block diagrams of thyristerized compensators. Okay, so they are saying you should do what? You should be able to sketch two things: basic topologies as well as the block diagram of what? Of thyristerized compensators and self-commutated compensators. So you should be able to do four things. Okay, what are these four things? You should be able to draw the basic topologies of a thyristerized compensator as well as a self-commutated compensator. Those are the two things. Then you should be able to draw the block diagram of the thyristerized compensator and the self-commutated compensator. Those are four things. That's the first point. Okay, what is the second point? The second point is you should be able to do the design calculations for a FC dash TCR. We should be able to do design calculations. Okay, right. Then the other thing is what? You should be able to derive an equation for the reactor current of a TCR. Okay, so there's some derivation involved. Then you should also be able to determine the required delay angle of a TCR to compensate for a specific reactive current. Okay, that's the learning outcomes according to the study unit. Okay, right. So now let's go. Introduction. To complete this unit, you should study the chapter on facts in your prescribed book. Okay, this is the study guide and it is referring us back to the book. Okay, now what do we mean when we say a study guide? This means this is just a summarization, or it's a summary of what's in the book. Okay, so let's continue. In the study unit, we will explore reactive power compensation technologies. So we are going to explore what? Power compensation technologies, specifically looking at reactive power and the focus on a few applications to improve our insight into the way reactive power, meaning the VAR component of the power diagram, okay, can be utilized to improve power factor, which is 1, control power flow, which is 2, and then improve the voltage regulation and so forth. Okay, right. The compensators are roughly divided into the following two groups. What are these groups? It's the compensators that utilize thyristors and thus rely on the current flow to drop to zero for the thyristor to switch off. These are referred to as thyristerized VAR compensators. Okay, now compensators that utilize IGBTs and IGCTs. These devices have a gate terminal that allows for turn on and turn off via a control voltage. Okay, these are referred to as self-commutated VAR compensators. Now obviously this is a point where you can easily miss it, so we are going to go through it again. Compensators that utilize your IGBTs and your IGCTs. Okay, now when we say IGBTs, what are we referring to? We are referring to the insulated gate bipolar transistor. And your IGCTs, it just means integrated gate, not insulated gate, integrated gate, commutated thyristor. That's it. So the one is a what? A transistor, bipolar transistor. The other one is a what? Commutated thyristor. These devices have a gate terminal, as we've just established. That's what the G in IGBTs and IGCTs. That's what it means there. It has a gate terminal that allows for turn on and turn off via a voltage control. Okay, simply meaning you'll be able to switch off and on using voltage control applied to your gate terminal. Okay, then it continues by saying these are referred to as self-commutated VAR compensators. Self-commutated, imagine that. Okay, so now let's continue now. Let's continue. Okay, right. It says here, the basic thyristerized VAR compensators are the thyristor controlled reactor and the thyristor switched capacitor. The basic topologies are as follows. You have your TSC as well as your TCR. What is your TSC? Your TSC, it is your thyristor switched capacitor, and then you also have your thyristor controlled reactor. The reactor simply refers to that coil, okay, and then your capacitor, it refers to this coil. And as we've noticed, we have a DI/dt limiter. Now what does that mean? That just simply means that it limits, or it, for now I'll say limit. Limit is not the right word, but for now I'm going to say it limits the change in current flow. The change in current as a function of time in this branch. Okay, but anyways, that's just to give you an example of what we mean when we talk about a DI/dt limiter. Yes. Inductor, it's a device where it just, I don't want to say that it resists or it limits, but if I say the word resist, if I say the word limit, it's going to make sense. It resists the sudden change in current flow. It opposes the variation, that change in, or it, I don't want to say deteriorate, but okay. So that essentially is what's happening here. The basic thyristerized VAR compensators are the thyristor control, meaning you have your basic thyristerized VAR compensators. You have them, okay? And these are two examples of thyristerized VAR compensators. It's your TSC as well as your TCR. These are the topologies, okay? All right. So now let's continue now. Sometimes a fixed capacitor, meaning FC